Somewhere between 400,000 and 1 million years ago, a human ancestor figured out how to control fire. They did not know they were doing chemistry. They did not know that combustion is a rapid exothermic reaction between fuel and oxygen, releasing carbon dioxide, water, and a large amount of heat. They just knew fire was warm and kept predators away. They were chemists. Every time you breathe, dissolve sugar in water, rust a nail, or cook an egg, you are doing chemistry. Chemistry is not a subject confined to labs and schools. It is the description of matter changing into other matter. It is why iron turns red when left in rain, why bread rises, why antacid tablets fizz, why explosives explode. The entire material world, every substance you have ever touched, every transformation you have ever witnessed, is chemistry. This is all of it, in 20 minutes. To understand chemistry, you start with a question that seems too simple. What is everything made of? Ancient philosophers guessed. Empedocles proposed 4 elements: earth, water, fire, and air. For 2,000 years, with occasional modifications, this is roughly where Western natural philosophy left the question. Gold was special because gold was gold. Explaining its properties by reference to mystical essences was considered sufficient. Alchemy tried harder. Medieval alchemists attempting to transmute lead into gold became accidentally competent chemists. They developed distillation, acid synthesis, and the beginnings of systematic experiment. They never made gold. They laid the groundwork for everyone who came after them. The first modern crack arrived in 1661, when Robert Boyle published The Sceptical Chymist. He rejected the 4-element theory and proposed that elements should be defined by what they actually are, substances that cannot be broken down further by chemical means. Not philosophy, experiment. The next crack was larger. In 1789, Antoine Lavoisier published the first modern chemistry textbook and along the way burned the old system down. He named oxygen and hydrogen, discovered that water is not an element but a compound of 2 of them, showed that combustion is not the release of a mystical substance called phlogiston, but rather a reaction with oxygen, and established that mass is conserved in chemical reactions. Matter does not appear or disappear, it rearranges. The total mass before equals the total mass after. This law of conservation of mass is still the foundation of every balanced chemical equation. Lavoisier was guillotined in 1794 during the French Revolution, accused of tax fraud. The judge reportedly said the Republic had no need for scientists. In 1803, John Dalton proposed that elements consist of atoms, tiny, indivisible particles, and that different elements have atoms with different masses. He constructed the first table of atomic weights. For the first time, chemistry had a framework for counting things. When hydrogen and oxygen combine to form water, 2 hydrogen atoms bond to 1 oxygen atom, always, with no exceptions. Chemistry stopped being a collection of observations and started becoming a science that could predict. By the mid-1800s, chemists had identified 60-something elements and noticed something strange. When you arranged them by atomic weight, properties repeated. Every 8 elements, something similar appeared. Lithium, sodium, and potassium are all soft metals that react violently with water. Fluorine, chlorine, and bromine are all reactive gases. The periodicity was real, but nobody could explain it. In 1869, Dmitri Mendeleev arranged the known elements in a table ordered by atomic weight and recurring properties. Where the pattern required an element that had not yet been found, he left the gap and predicted its properties. Gallium was discovered in 1875, germanium in 1886. Their properties matched Mendeleev's predictions with eerie accuracy. The table was not a description, it was a map, with blank spaces waiting to be filled. Modern understanding explains why the pattern repeats. Atoms have electrons arranged in shells and orbitals around a nucleus. The outermost shell determines how an element behaves chemically. Elements in the same column of the periodic table have the same number of electrons in their outer shell. Sodium and potassium both have 1 outer electron. Chlorine and fluorine both have 7. The chemistry follows the outer electrons, not the nucleus. The periodic table has another layer of order beyond columns. Moving across a row from left to right, atomic radius shrinks, because you are adding protons to the nucleus without adding a new electron shell, pulling the electron cloud inward. Ionization energy, the energy required to rip an electron off, increases moving right, because the nucleus holds its electrons more tightly. Electronegativity, the tendency to pull shared electrons toward itself in a bond, follows the same pattern. Fluorine, top right of the table, is the most electronegative element. Cesium, bottom left, gives up its electrons most easily. These trends are not rules someone memorized. They follow directly from the structure of atoms. This is where chemistry connects to quantum mechanics. Electrons do not orbit nuclei in neat circles. They occupy probability clouds called orbitals, each with a specific shape and energy level. When quantum mechanics was worked out in the 1920s, it finally explained why the periodic table looks the way it does. The shells fill in a specific order. Elements with full outer shells, the noble gases, are chemically inert. Elements 1 electron short of a full shell desperately want to grab an electron from somewhere else. That desperation is the source of most of chemistry's action. Atoms bond when it lowers their energy. There are 3 main ways they do it. Ionic bonding happens when an atom with too few outer electrons gives 1 or more to an atom that is short. Sodium, with 1 outer electron it would rather not have, donates it to chlorine, which needs 1 more. Both end up with full outer shells. The sodium becomes positively charged, the chlorine negatively charged, and opposite charges attract. The result is sodium chloride, table salt, a hard white crystal with a regular lattice structure. The bond is not between 2 specific atoms. Sodium and chlorine arrange into an extended grid, each sodium surrounded by 6 chlorines, and each chlorine surrounded by 6 sodiums, the whole structure held together by electrostatic attraction. Covalent bonding happens when neither atom wants to give up its electron entirely, so they share. 2 hydrogen atoms, each with 1 electron and wanting 2, share their electrons so each feels like it has a full inner shell. The electrons spend time between both nuclei, pulling both nuclei toward the center. The result is a hydrogen molecule. Carbon, oxygen, nitrogen, sulfur, most of the elements that matter for life, bond covalently. A covalent bond is a shared pair of electrons. Double bonds share 2 pairs. Triple bonds share 3. Carbon can form 4 covalent bonds simultaneously, which is the root of almost everything interesting in chemistry. Metallic bonding is different. In metals, the outer electrons are so loosely held that they detach entirely and flow freely between atoms. The metal becomes a lattice of positive ions swimming in a sea of free electrons. The electron sea can move in response to electric fields, which is why metals conduct electricity. It can also carry heat, which is why metal handles burn your hand. The lattice can shift and slide without breaking bonds entirely, which is why metals are malleable. They can be hammered into sheets without shattering. Water deserves special attention. A water molecule is 2 hydrogens covalently bonded to 1 oxygen. Oxygen is much more electronegative than hydrogen. It pulls the shared electrons closer to itself. This makes the oxygen end of the molecule slightly negative and the hydrogen ends slightly positive. Water is a polar molecule. Polar molecules attract each other. The positive hydrogen end of one water molecule is drawn to the negative oxygen end of another. These attractions are called hydrogen bonds. Individually, each one is weak. Collectively, they make water liquid at room temperature, give it an unusually high boiling point, make it expand when it freezes rather than contracting, and make it an excellent solvent. Every biological process that involves water depends on hydrogen bonding. There is a weaker version of intermolecular attraction that affects everything beyond polar molecules. Electrons are never completely still. They shift around randomly within their orbitals. At any instant, one side of even a non-polar molecule has slightly more electrons than the other, creating a temporary dipole. This temporary dipole induces a dipole in the neighboring molecule, and the two attract briefly before the electrons shuffle again. These are van der Waals forces, or London dispersion forces. They are individually weak and temporary. Their strength scales with the number of electrons, which is why large molecules like fats are sticky and have high melting points, while small molecules like methane are gases at room temperature. Every molecule in your body interacts with every other molecule through some combination of hydrogen bonds, ionic attractions, van der Waals forces, and covalent bonds. Now carbon. Carbon has 4 outer electrons and wants 8, so it forms 4 covalent bonds to get there. It can bond to itself, forming chains of any length. It can form rings. It can form branches, double bonds, and triple bonds. No other element produces anything close to the structural diversity that carbon does. Silicon, directly below carbon in the periodic table, can also form 4 bonds, but silicon bonds are weaker. And silicon-oxygen bonds are so strong that silicon chemistry locks up into rocks rather than producing complex fluid structures. Life on Earth is carbon-based because carbon is the only element that can form the required variety of stable, complex structures at the temperatures where water is liquid. Organic chemistry is the chemistry of carbon compounds. There are roughly 10 million known organic compounds. Every living thing on Earth is built from a relatively small set of carbon-based building blocks: amino acids, sugars, nucleotides, fatty acids. Proteins are long chains of amino acids. DNA is a double helix of nucleotides. The specific sequence of nucleotides in DNA encodes the instructions for building proteins, and proteins run the cell. All of this, the machinery of life, is organic chemistry. When carbon bonds are adorned with other atoms or groups of atoms, the properties change dramatically. A hydroxyl group, an oxygen bonded to a hydrogen hanging off a carbon chain, makes an alcohol. Ethanol, the alcohol in drinks, is a 2-carbon chain with a hydroxyl group. The same carbon chain without the hydroxyl group is ethane, a flammable gas. One functional group, completely different properties. Carboxylic acids have a carbon double bonded to one oxygen and single bonded to another oxygen that carries a hydrogen. Amines have nitrogen. Aldehydes, ketones, esters. Each functional group gives organic molecules a distinct set of chemical behaviors. Organic chemistry is largely the study of how these groups are attached, rearranged, and transformed. The simplest organic molecules are hydrocarbons. Carbon bonded to hydrogen and nothing else. Methane is 1 carbon and 4 hydrogens. Propane is 3 carbons and 8 hydrogens. Gasoline is a mixture of longer chains. Burn any of them and you break the carbon-hydrogen bonds and form carbon dioxide and water, releasing the energy stored in the bonds. Your body does something similar, more slowly and under careful enzymatic control when it metabolizes glucose. Every chemical reaction comes down to breaking some bonds and forming others. Energy is required to break bonds. Energy is released when bonds form. If the bonds you form are stronger than the bonds you break, the reaction releases energy overall. It is exothermic. Combustion, explosion, your cellular respiration, all exothermic. If forming the new bonds requires more energy than breaking the old ones provides, the reaction absorbs energy, endothermic. Dissolving ammonium nitrate in water is endothermic, which is why it cools, which is why it is in instant cold packs. Whether a reaction will happen at all depends on 2 competing factors. The first is enthalpy, the energy difference between products and reactants, which drives reactions toward lower energy products. The second is entropy, the universe's preference for disorder. These 2 factors combine in a quantity called Gibbs free energy. A reaction is spontaneous only if it reduces the system's free energy. Sometimes a reaction is energetically favorable, but entropically unfavorable, or vice versa, and the balance between them determines whether it runs. Many reactions do not go to completion. They reach equilibrium, a state where the forward reaction and the reverse reaction proceed at the same rate, so the concentrations of reactants and products stop changing. This is not a stopped reaction. Molecules are still converting in both directions. The net change is 0. A reaction's equilibrium constant tells you where the balance lies. A large constant means products dominate. A small constant means reactants dominate. The Chaffeier's principle says that if you disturb an equilibrium by adding more reactant, changing the temperature, or increasing pressure, the reaction shifts to counteract the disturbance. Industrial chemistry relies on this constantly. The Haber process, which makes ammonia from nitrogen and hydrogen for fertilizers, uses high pressure and moderate temperature to push equilibrium toward the product. Without ammonia fertilizer produced this way, roughly half the current human population could not be fed. The Haber process is arguably the most consequential chemistry ever industrialized, but spontaneous does not mean fast. Diamond is thermodynamically unstable relative to graphite at room temperature and pressure. Diamond should spontaneously convert to graphite. It does not, because the path from diamond to graphite requires breaking and reforming extremely strong covalent bonds, and there is not enough thermal energy at room temperature to get over that barrier. The activation energy is too high. This is good news for anyone who owns a diamond. Catalysts work by lowering activation energy. A catalyst provides an alternative reaction pathway with a lower barrier. It participates in the reaction, but is regenerated at the end, so it is not consumed. Enzymes are biological catalysts. Every reaction in your body, the breakdown of food, the copying of DNA, the repair of tissue, is catalyzed by a specific enzyme. Without enzymes, nearly every biochemical reaction would happen too slowly to sustain life. Acids and bases are chemistry's most useful pair of opposites. An acid donates a proton, a base accepts one. When hydrochloric acid dissolves in water, it releases hydrogen ions, bare protons, into solution. pH measures the concentration of hydrogen ions on a logarithmic scale. Pure water is pH 7. Stomach acid is around pH 2, 10 million times more concentrated in hydrogen ions than water. Bleach is around pH 13. The logarithmic scale means that a change of 1 pH unit represents a 10-fold change in concentration. The entire range, from lemon juice to drain cleaner, spans about 12 units. The explosions. An explosion is a very fast exothermic reaction that produces a large volume of gas very quickly. Gunpowder is charcoal, sulfur, and potassium nitrate. When ignited, the reaction produces carbon dioxide, nitrogen, and potassium sulfide, releasing enormous amounts of energy. The gas expands faster than sound, producing the pressure wave. TNT, nitroglycerin, and modern military explosives work on similar principles. Molecules packed with nitrogen and oxygen that decompose violently, releasing nitrogen gas, water vapor, and carbon dioxide while generating more heat than the surroundings can absorb. Polymers are another place where chemistry becomes engineering. A polymer is a long chain of repeating molecular units called monomers. Nylon, polyester, PVC, rubber, polystyrene, all polymers. The properties of a polymer depend on the chemical identity of its monomer, the length of the chains, and how the chains interact with each other. Short chains are liquid or waxy. Long chains are solid, rigid, or flexible depending on how tightly they pack. Chemists can now design polymers with specific properties: heat resistance, flexibility, optical clarity, conductivity. The plastics in every object around you are the result of chemistry precisely controlling what atoms are bonded to what. So are the synthetic fibers in your clothes, the adhesives holding your phone together, and the coating on your nonstick pan. Chemistry meets physics at the atomic scale. The periodic table is explained by quantum mechanics. The strength of bonds is explained by electrostatics. The rate of reactions is explained by statistical thermodynamics. At the frontier, chemistry and physics blur into physical chemistry and quantum chemistry, calculating the behavior of molecules from first principles. Some of the most complex calculations in science are attempts to model protein folding, the process by which a chain of amino acids spontaneously collapses into a precise three-dimensional shape that determines its function. The shape dictates the function. Getting the shape wrong is how diseases like Alzheimer's and Parkinson's develop. Chemistry is the science of transformation. It started with fire, and it ends at the edge of what we can compute. Every drug ever made, every material ever synthesized, every reaction that sustains your body right now, all of it is electrons rearranging themselves into lower energy configurations, bond by bond, one reaction at a time. And that's all of chemistry. Every substance, every reaction, every explosion, and every breath. In about 20 minutes. You're welcome.